Hi, this is my fifth lab for Physics 2211, the falling slinky. The objective of this lab is to observe and model the motion of a falling slinky. We'll be using Tracker and GlowScript to do so. Then we will compare the observations to the computer model we create in GlowScript, and we will use physics principles to explain our findings. The physics principles that will help guide us through this experiment, starting with the momentum principle. With our initial conditions where the bottom of the slinky is not moving, F net equals 0 and is equal to the sum of the force of gravity and force of tension. The momentum principle tells us that neither position nor velocity will update. As you look at the formulas on the right that tell us change in velocity equals F net over m times delta t. Since F net equals 0 in this case, we'll have no change in velocity. And when you go down to the position update formula, since the change in velocity is 0, our change in x will also be 0. For the conditions when the bottom of the slinky is moving, net force equals force of gravity plus F drag, and this will not equal 0 until terminal velocity is met, which will then have net force of 0. And the momentum principle tells us that velocity and position will update up until terminal velocity is met, since delta v equals F net over m times delta t. So when F net is a non-zero value, we will have a change in velocity, and then this will extend to the position update formula, giving us a change in position as well. For the force of drag, we'll be looking at this because we'll be looking at terminal velocity, which will tell us when the velocity will no longer be changing as the slinky falls, and drag increases proportionally to velocity squared, so it ends up equaling out with F grav at some point, making F net equals 0, and we'll get this drag force by taking physical constants to get the constant value b, and we will multiply this by velocity squared to get our force of drag. If we take a look at the tracker data, we can see that I used the YouTuber from Veritasium as the scale. He said on Twitter that he's 1.75 meters tall, so I used that as a scale. And then from there we tracked the bottom of the slinky over time, and as you can see, for the first 0.7 seconds or so, the bottom of the slinky does not move, and then it does begin to move. It first accelerates, and then it has a somewhat constant slope, kind of alluding to the fact that it is falling and then reaches terminal velocity and doesn't really continue to accelerate. Look at the GlowScript code used for the computer model. A Google search tells us that the mass of a slinky is about 0.25 kilograms. The initial position is about 0.494 meters off the ground with no initial velocity. The delta t is about 150 frames per second, or 1 divided by 150. And then our variable b used for the force of drag is about 2.5, given when we multiply density of air, cross-sectional area, and a few other physical constants. And then the force of gravity is the slinky's mass times g times negative j hat, which is a negative y direction. And then the force of tension is the opposite of the force of gravity, because we know that net force is 0 with the initial condition. And we're going to take a look at our code. We split it up into two parts. When time is below 0.8 seconds, that's the time during which the bottom of the slinky is not moving. And from that point until 1.4 seconds when it hits the ground, that is when the bottom of the slinky is moving. So we split it up into these two different loops because there are two different conditions for these different circumstances. So for the loop before 0.8 seconds are elapsed, you can see we have the momentum principle, but it will not really be in place here, or it will not lead to any velocity or position update because the net force is 0. So really for these first 0.8 seconds, since F net we have as F grav plus Ft, which are really just opposites of each other, it equals out to 0, so there ends up being no update in velocity or position. Second loop, our net force changes to force of gravity plus force of drag, which we get by multiplying the constant b by velocity squared, and then in the positive j hat direction. And we plug this net force into the position and velocity update formulas using the momentum principle, and we will end up seeing that during this time period, the velocity and position do end up changing, and the velocity ends up not changing after terminal velocity is reached. Now, as you can see in this slide, we're comparing the results of position versus time at the bottom of the Slinky between our glow script model and the tracker data. And you can see on the model, it starts off constant, just like the tracker data does, and it starts to accelerate downwards, and then it reaches a constant velocity. And the observed model shows a similar pattern as well, accelerating downwards and then reaching a somewhat constant slope, meaning that it reached terminal velocity just like we predicted it would in our computer model.